Right. Now we will move on to using two text processing libraries, namely NLTK and spaCy. And before you can use them, these are some of the libraries that you would have to install. If you're using pip, you can install pip, you can use this particular syntax. And some of these models also need certain downloaded models for them to function, right? So for especially for spaCy, before you can effectively start using spaCy, you need to download certain models, right? For example, since we are dealing with predominantly with English here, you have to download a model that is necessary for processing English data, and the name of the model is this. If you go back to spaCy's documentation, you will see that there are a bunch of models. They might be differing on size, they might be differing on the language, or they might be differing on the nature of the text that they have been trained on. But yeah, so let's dig a bit deeper into NLTK. NLTK is very popular text processing toolkit. It is something that is built keeping NLP research in mind, and this is very popular among NLP researchers. So let's look at some of the simple functionality that it offers. So once we, let's say, go back to the JSON example, once you read the text from that JSON, you can see that it's essentially you have a long string like this, right? But before you can get it to a processing pipeline, you need to break it into its components, right? And that's where tokenization comes into picture. So tokenization is nothing but breaking down a string into its constituents. Constituents are here, let's say, words or tokens for us. So NLTK has an inbuilt tokenization function called word_tokenize, and you can use them, and you can see that it breaks it down into its subcomponents. This is very simple here because you can also do the same for you can also break the string into its subcomponents using the split function, right? A few cases down we had seen the split functionality. So you can use text.split and you can split it wherever there is a white space, right? But tokenization is a bit more, it has a bit more nuance. For example, here the currency symbol $12, right? What NLTK's inbuilt function did is that the $12 was broken into two components, right? The dollar symbol, the currency symbol, and the value. Whereas if you were to just split the string based on white space, this will not have been the case, right? So it's a very good question at this moment to ask, how do I tokenize a string, right? Do I split at white spaces, or do I use a word tokenize like this? The answer, a very simple answer to this, is that it is very application dependent, right? For example, if you are dealing with financial data and you are interested in what all currencies are used in your document, then you might want to tokenize your text like this, right? So that you can take out the currency symbols and process them however you want to process them. If your functionality does not need that, if your application does not need that kind of that depth of splitting, then you can just use white space, right? And down the line we will actually end up seeing some of the tokenization methods that are very specific to social media, right? Because social media is very different from the kind of text that you would see in, let's say, a news article. So a tokenization, that method that works very well on news article, might not translate very well when it comes to social media text, right? So it is tokenization, simply put, is very application dependent and depends on what you want to keep and what you want to remove from the data, essentially. So this is a simple word tokenization. You have one string and you're breaking into its subcomponents. But let's say if you have a paragraph and you want to break it into its individual sentences, and the library that you use is and the function that you use is sentence tokenization within an NLTK library. So you had two sentences here, and by using the send token functionality, you can break them into two things. And you can again call the word tokenize on each of these sentences individually, and you will get tokenized sentence for each of these sentences. Yeah. So let's look at a few more cases of tokenization, few more ways of doing tokenization. As I said here, you are in this case using word tokenizer, you are using an inbuilt function of NLTK. Let's say that it does not serve your purpose. You need to be a bit more. You need to be a bit more. You need to have a bit more control on the tokenization process. Let's say. In such cases, you can write your own patterns based on which the tokenization is happening, right? One way of doing this is utilizing the regular expressions, right? So if you're unaware of what regular expressions are, I would request you to go back and read up a bit more on that. But to simply put, they are essentially patterns which are useful in for example, breaking down a text into components, right? So a very simple use case is here, where you are iterating over these three articles. You have three strings essentially, and you're saying that for each of those strings, I am going one by one, and I am splitting them based on a pattern, right? So and the way you write these regex patterns is a class of its own, let's say. But so that's why I would request you to go back and brush up on or read up a bit more on how do you write these regular expressions. But the pattern present here, what is it saying is that I want to split wherever there is a full stop, wherever there is an exclamation mark, and wherever there is a question mark, right? And so the piece of code that is present in this cell is iterating over all of these articles one by one, and it is splitting them into components based on this pattern, right? And you can see that I'm printing each of these sentences here based on how I had split them using the regular expression here. You can see that sentence 0 is this, sentence 1 is the full stop on its own, sentence 2 is the whole sentence again, sentence 3 is full stop on its own, right? So this particular piece of code re.split, re is the library for regular expressions in Python. So re.split is taking a pattern, and it is taking the document it needs to split as an argument, and it splits into its two components, and it is splitting the full stop as a separate entity and storing it, right? And if this is the string here, you can see that we are saying that you split at every full stop, exclamation, and question mark. You can imagine what could happen here, right? So this exclamation mark, this is where it will be split once, this is where it will be split again, and wherever one of those three elements occurs, it will be split, right? And you can see that it's split as you instructed it to be split, right? But again, if you were to not do that, if you didn't want to do regex based splitting, regular expression based splitting, and just use the inbuilt sentence tokenize, you can see that it breaks up the sentence much more nicely, much more intuitively, and this is what you would want, right? Now let's look at another example of regex. So let's say you want to tokenize this text, and we will look at some of the patterns, an example way of how you can use a regex regular expression based tokenizer. So this is again like a pattern that we wrote here, right? The pattern that we wrote here, we're saying that this is the pattern. It's either a full stop, exclamation mark, or a question mark, right? And this is a much more complexer pattern, right? I have also commented it for your benefit. Let's say that if you want to keep the abbreviations together, this is the pattern you would end up writing. And if let's say if you want to keep the percentages and the currencies together, this is what you would end up writing, right? So here you have tokenized the same text, this particular text, using both the methods. One is the NLTK's word tokenize method, and the other one is the regex based tokenizer method. And you can see the only difference between them is how dollar is treated, right? So word tokenize is splitting them, and the currency symbol is split from the value, whereas in the regex method we said that we don't want to do that. We want to keep them together, right? And and this is how you achieve that. So the only point that I'm trying to make with this particular example here is that tokenization, as I said, is very application dependent, and if you come across a use case or in your application you do not have any inbuilt method that does a string tokenization exactly how you want it, you can write these regex patterns and use them to tokenize your text. And this could be of whatever complexity complexity and type that you need. Right. So let's move on to the next particular topic within this. This is where we are discussing a topic called stop words. Stop words are words which are probably not necessary for your processing, right? Stop words are not exactly same for all the applications, but stop words as a concept is just this list of strings that do not, let's say in your opinion, do not add a lot of value to your problem statement or your text corpus, so you might as well want to drop it, right? So for example, in your string I am going to eat, let's say the word token to, it's a preposition and it's not, let's say you have no need for such a token, right? Or I am this, for example, another sentence was this is a laptop, right? This is a laptop. For example, the token a or the word a is, let's say it's not adding a lot of value in your application and you want to drop it just to save space. Let's assume that's what you want to do. You want to drop unnecessary token so that you end up with a much smaller data that you can process. In such a case, you can use the concept of stop words and remove them as you would want. Now stop words, as I said, could vary application to application, could vary language to language, and you can use the inbuilt stop words that is there in NLTK. NLTK already maintains a list of stop words. You can use them, you can add to them, or you can create your own stop words entirely, right? But at the end of the day, it is one thing that you would need if you want to remove unnecessary tokens or unnecessary strings that are not adding a lot of value to your problem, and you can just remove from your text, right? In this string, what we are doing is that we are dropping all the stop words from the sentence, right? So we will keep it if the word is not in the stop words list, right? And the stop words list is what we are taking from NLTK library. We can create our own as well, right? Another important concept in NLP is pause tagging, part of speech tagging. For example, if you want to understand which word is a noun, which word is a verb, right? For example, one use case of this could be you are given a news article, and if you want to extract the name companies name, all the companies names that are mentioned in a text article. In such a case, knowing what is a pause tag of a particular token is a very useful information to have. For example, if it's the name of the company, it is likely to be a noun, right? It is a noun. It's a proper noun. So you can use pause tag as information to retrieve that data, if that is the use case, right? So NLTK has an inbuilt pause tagger for English, and you can see that once you pause tag the data, it gives a tag, it gives a parts of speech tag to each token, right? So NN is a noun, NNP is a proper noun, and this is a determiner, tutorial is a noun, right? Another concept that is related to pause tag is the concept of chunking. Chunking is where a sequence of tokens are acting as one unit, right? An example of this could be I am eating a yellow mango, right? Now a yellow mango is one unit, right? Is a determiner, yellow is a the adjective of the noun mango, and mango is the noun itself, right? A yellow mango. While these are three separate tokens, they have their own pos tags, but they are playing a role of an object in the whole sentence, right? So a yellow mango could be used as could be thought of as one unit in that sentence, right? And this is the notion of chunk. So chunk is basically a group of words that are playing a specific role in a sentence. And you can use you can do chunking based on certain rules that you can write on your own, right? So this is the chunker that is rule based, and you have written the rules here, right? So this is the a pattern that you would write for extracting the nouns, the noun chunk, the verb chunk, the adjectival chunk, and stuff like that. So once you let's say use this syntax to chunk your sentence, it will look something like this, right? So this my chunk that you're seeing here, that is what is chunked as a unit here. So whatever is within these brackets, right? My chunk is one chunk, right? So learn NLP is one chunk, tutorial is another chunk, right? And this depends on all the rules that you write, but this is again a rule based thing. There are other alternatives to this as well, where there are more machine learning based methods also, where you don't have to write these rules on your own, but such patterns are learned over a data, annotated data, and you can use them. But what I'm showcasing here is just an example of how you can use regex based patterns to chunk your data. Right. Another very important concept is lemmatization and stemming. Right. So for example, let's say there are words like this, right? Wait, waiting, weighted, weights, right? There is a base word wait, and there are suffixes that are added to words, right? Waiting, weighted, weights, and those suffixes in this case at least are denoting the tense, right? Weighted is the past tense, weights is present tense. Now in such cases what happens is, but if you were to count these words, right? Let's say you have a very large collection of strings, and you're counting which word has occurred how many times. Now wait will be counted as a separate token, waiting will be counted as separate token, and all of these variations of the word wait will be treated as separate tokens, right? So they will be counted separately. Whereas you are more interested, probably you're more interested in counting that base form, how many times a word wait, doesn't matter in which suffix, how many times that word wait has occurred, right? So in such cases you will end up using one of these two methods, a stemmer or a lemmatizer, right? So broadly what they do is they break down the sentence, they reduce the word to its base form, right? So for example, waiting will be reduced to wait, right? Because that is the base form. Weighted will be reduced to wait, weights will be reduced to wait, right? So all of these 4 tokens will be counted as one, right? So Porter stemmer, again an inbuilt functionality of NLTK, could be used to do that, right? So you can see that using Porter stemmer, I'm stemming it to its root form, and you can say waiting is reduced to wait, right? So this is a simple example. Another way of doing this is something called a lemmatizer, right? Lemmatizer also is doing the same. Studies is reduced to study, studying is reduced to studying, cries is reduced to cry, cries again anyway cry, right? So what is the difference between lemmatizer and stemmer, right? The only difference between these two is how they do it, how they reduce a token to its base form. WordNet lemmatizer is more a rule-based approach, where you have created a knowledge base of cries. Let's say you have stored all the information, like cries will be reduced to cry, studying will be reduced to study. This is more rule-based, and it's a knowledge-based method. Whereas stemmer would be a more statistical method, right? So you have using statistical methods, you have learned the base forms of many tokens, right? So studies, for example, will be reduced to studi by a stemmer, right? So again, this because it is statistical based. Let's say in this case, it has learned that s is a separate is a suffix, right? So if I want to reduce a word to its base form, I'll just remove that suffix. So studies, from studies I'll remove a suffix like s, right, which is in many cases a plural suffix, right? So it has based on a certain corpus, stemmer has learned patterns like this and the statistical patterns like this to reduce word to its base form. So again, as I said, the difference between lemmatizer and stemmer is this: how they have learned to how they reduce a word to its base form, and because of that, stemmers are not always bound to give you a word that exists in a dictionary, right? This is a good example here, right? Studies is reduced to studi, right? Studi is not a it's not a proper vocabulary English word, right? But there are disadvantages and advantages to both of these. WordNet lemmatizer, while it returns proper tokens, it is sometimes slow, and sometimes a word, for example, a new word comes up that is not there in the knowledge base that you created, right? For example, Christ was not there, let's say, in the resource that you created, right? In such case, it will break down. It will not be able to lemmatize it properly. That is the advantage and disadvantage of lemmatizer. Stemmer, on the other hand, it's bound to give you some output. It has broad coverage. It's very unlikely that it will break down for any of the input. But on the other, that while that is a advantage, there is a disadvantage that it is not always bound to send you or return a token that is a valid vocabulary dictionary term, right? So these are some of the things that you would want to keep in mind. Another concept in NLP is something called WordNet. WordNet is basically, again, a knowledge base of where you have collected these resources, like which word is related to which word, right? So these are organized in these sets called synsets, and an example here is like I'm picking the synset for dog, right? And you can see that it comes up with all the dogs that are all the tokens that are related to this particular word dog, right? And one of the use cases of such a resource is that you can create a list of synonyms and antonyms, right? For example, for the word active, you can create a list of synonyms and antonyms based on WordNet, right? So dynamic, participating, fighting are all synonyms of active, and stative, quiet, extent are all the antonyms of the word active. Now this is only possible because you have a knowledge in that is encoded in WordNet, which organizes tokens in terms of related tokens, right? But again, since it's a manually created resource, you might end up in a case where the token that you're dealing with is not present in the synset, right? Again, that is something that is a disadvantage of most of the rule-based methods. While they do very, very well for what they have already seen, they might not have a large coverage, in the sense that they might not have all the tokens that are known to mankind in their knowledge base, right? There might be some gaps, right? So I think the last component that we will see in NLTK is this thing called frequency distribution, and this is very important tool if you want to understand which token has occurred how many times in my large corpus, right? While it's a very simple concept and it could be used, it could be done by writing your own piece of code, and it will not be very long, but this is, let's say, a very code light way of doing the same thing, right? So you read a large text file, and you take the top, let's say in this case I'm taking top 2000, I'm taking lines from 2700 onwards, because in this text file what is happening is this is a novel, and I am removing the first few lines because they are stuff like table of contents and all that. So I'm keeping lines only from 2728 onwards, right? This, if I'm not wrong, is a collected works of Shakespeare. So basically, let's look at how frequently Shakespeare uses which word, right? If that is something of interest, this could be quite useful. So now you can very quickly do this using this functionality called frequency distribution. What it needs is a list of tokenized sentences, right? So word tokenized of lines. If it is given as an input to this, you can see it creates a dictionary of which token has occurred how many times, right? So you can easily plot them, and you can see that these punctuations have occurred like this, and there are these words like the, and, of, to, etc., etc. And how a frequency distribution looks is something like this, where you have a token followed by the count, key value pairs again, token followed by count, token followed by count, right? And if you want to pick the top most common, let's say top 50 or top 100, you can use this function called most common followed by the number, right? Now this is a good place to discuss why we were dealing with cleaning of a text, why were we dealing with how to draw punctuations, why were we dealing with how to drop stop words, right? You can see that because these are some of the string tokens that are used very frequently, they will be very common in every corpus, right? But they do not bring a lot of information about the corpus, right? For example, if I'm asking this question, which token did Shakespeare use the most, or what kind of tokens, or what were the tokens that he used the most, and you just pick the top 100 or 20 tokens and you print, you can see that they are tokens like this, like full stop, comma, the, and, right? And this would be the case with anybody. Even if you take a list of sentences that were probably written by Mahatma Gandhi, this would essentially be the same there as well, right? So this is why cleaning your text and cleaning your stop words is a useful thing to do, right? This is a demonstrative example for that. But yeah. Yeah. Like we were dealing with tokens, sometimes you want to deal with group of tokens. Let's say you want to deal with bigrams, right? Bigrams, trigrams, 4 grams, 5 grams, right? This is basically combination of 2 words, 3 words, 4 words, and 5 words, right? And this is what it would look like: the period it was, right? So it is basically breaking down the whole sentence into collection of two words, like a sliding window of 2. A sliding window of 3 would be a trigram, sliding window of 4 will be a 4 gram, etc. But yeah, so if you want to go beyond token, you can use this bigram functionality, trigram functionality. Right. Start. So far we have looked at a library like NLTK. While it offers very basic functionalities, but those are some of the functionalities that you are most likely to use very frequently, right? Now we'll look at a library called spaCy. This is a library that was built with well, I said NLTK was built mostly keeping research in mind, keeping research in mind, while spaCy was built keeping industrial applications in mind, right? So it is like a model that you can use for your production models and stuff like that. So yeah, so I think I covered the way you install spaCy and the way you download spaCy models in the earlier cells. But before you proceed, I think you should complete the installation of spaCy, install the necessary modules, and then take it from here. So this is a very simple example of I am loading a model for English, loading a spaCy model for English. I am taking a string like this and I am processing it to extract certain features out of the data, let's say, right? And you can see that it's very simple the way whatever we have discussed, many of the things that we have discussed so far, the lemmatization part or the pause tag part, or the, let's say, the chunking part, most of this could be done very easily with a simple 2 or 3 line code like here, right? So what is being printed here is for this particular doc, for this particular sentence, you are printing the text, the lemma, the pause tag, and a few other features, right? So let's look how they look like, right? So each line is basically printing all those features for one token, right? So if your sentence is Apple is looking at buying UK startup for 1 billion, if this is your line, you're breaking down them into tokens, and for each token you have certain features, right? So the text of the token is Apple, the lemma is Apple again. What is the pos tag? It's a proper noun, right? NNP. What is the dependency? It's a subject, right? So while pos tag provides some information, what dependency dot dep underscore is providing is the dependency role in a sentence, right? So what is a dependency role? For any sentence, I think you can create a tree like this, right? So Los Angeles based Bell makes and distributes electronic products, right? If I think that is the sentence here, and you can see that if that is the sentence, if that's a very long sentence, you can see that there is a structure within that sentence, right? So there is a makes, that is basically a verb, and you can see that there is a subject. Subject is Bell, that is based in Los Angeles, right? And there is another word, distributes. Distributes also has a subject Bell, and it has a object products, right? Products of what kind? Computer products, electronic products, and building. So this is what we mean by dependency roles. You can see that you have broken down the sentence into its constituent tokens, and there is an arc linking the related tokens, and you will also have a relation for that arc, right? So makes and Bell are related, and the relation is a subject and subject, right? So all these roles are essentially defined. This is a tag set that is defined by language researchers and linguists. And what we are seeing here is that how do you extract those relations based on computational tools like spaCy, using computational tools like spaCy. And this detailed information about how a sentence is structured can be very useful if you are looking at extracting some useful information out of the data, right? So if you were to extract all the subjects, what you can do is you can create a tree like this and extract all the subjects, or you can extract all the objects, or you can extract for each object, let's say what were the modifying terms, right? Amod, let's say adjectival modifications, like computer, building, right? And if you want to, let's say Bell, where is Bell based on this tag preposition, in preposition, you can say that Bell is based on Los Angeles, right? Now this is made easy, very possible, because you can break down a sentence into a neat structure like this, insert dependency structure like this, right? This is called this act of breaking down a sentence into its roles is called dependency parsing. Right? And that is what end subject this particular feature is doing, token dot dep underscore, right? And you also have some other features like shape, is alpha, is stop. So shape is basically telling you whether which character within this is capitalized or not capitalized, right? And is alpha is basically saying whether it is alphabet or if it is let's say symbol like this, it will be false, right? And you also have whether it's a stop word or not, right? Is stop is basically that, right? So this is basically the capability of a library like spaCy, right? It can just by call of a simple function, it can give you very detailed information about the text, right? But there are, of course, I think one caveat for this is that these models are very mature probably for English, but if you're dealing with other language data, let's say you're dealing with Indian languages like Telugu or Tamil or English, this probably is not possible. Yeah. Right. Going back to, again, in this case, we are discussing a concept of chunking that we have seen earlier, where we had written rules to chunk a sentence. Here you are using spaCy library to do the same, and you are interested in noun chunks, right? Noun chunks, again, this is a problem of interest because in information retrieval, if you want to, as I said, in an news article, you want to extract all the company names that were mentioned in a financial news article. in such a case, if you are able to extract noun chunks, you are able to extract all the company names, right? So it's that simple. So for in many of these cases, noun chunks is the problem that is a bit sought out. So again, you can create noun chunks just by calling dog.noun chunks, right? So autonomous car shifts insurance liability towards manufacturers. If that is the sentence, there are noun chunks like autonomous cars, right? So yeah, and there are also noun chunks like insurance liability and manufacturers, right? So you can create the text, you can understand the root of the text, the dependency of that root head. So as we said, chunks are basically combination of tokens, right? So going back to the example we discussed earlier, a yellow mango, right? This is one group of chunk. This is a group of tokens, and it's a noun chunk. Now in chunks there is this concept of head as well, right? What is the head of that chunk? Head is basically the main token within that chunk, and in this case a yellow mango, a mango would be the head chunk, right? And yellow is something that is modifying that word mango. It's an adjective that is modifying the word mango, right? So that is what is meant by a root here, right? So every chunk has a root word, right? Right. Another thing that you might be interested in, just the entities, right? And all the entities need not necessarily be noun chunks. There might be entities that might not exist with that particular pos tag, right? So, and you might also be interested in what kind of entity are they? Are they an organization, or is it time? Is it money that is mentioned in that entity, right? So again, this is where you can use doc.ends, this particular functionality of spaCy, and you will see that for each token you get the start and end, start character, which is the starting position, ending position, and you also get a label, right, of whether it's an org, whether it's a geopolitical entity, or like 1 billion is tagged as money. So again, if you're interested in information retrieval, this makes your application a bit more smooth and a bit more straightforward. Right. So this is where we stop with NLTK and spaCy. So we'll do a quick recap. In the first set, we had looked at how do we read text from different sources, a JSON and a pandas. Second thing, we looked at some of the basic string manipulation methods that Python offers built in. Second, we looked at two libraries. One is NLTK and another is spaCy. Right? Going forward, we'll look at some of the pre-processing steps that are needed in the social media text. Right. So we already looked at, let's say, tokenization and cleaning based on stop words and everything, but now let's look at some of the pre-processing steps that are probably needed. Yeah. Right. So some of the steps that we looked at, like lemmatization, so that's what is called as normalization, right? So I think it's worthwhile to discuss why would you do and why would you not do lemmatization, right? So sometimes, as I said, if you want to count the number of tokens count the number of times a particular token has occurred, maybe it's useful to get good estimate of those counts to reduce the words to their base form, right? Weighting is reduced to weight, right? So when you generalize and you count all the times it has occurred, the number of times that weight has occurred, that count is represented a bit more robustly and faithfully. Another thing is that you do filtering, like you drop stop words and punctuations just to remove noise from your data, and this noise is again application dependent, right? For some of the applications you would want to drop out stop words, right? But for others you would want to keep those stop words, right? For example, if you're counting the words, might as well drop the stop words. But let's say if you're trying to take the dependency graph like this from the sentence, right? If you drop the stop words and you give it to the same model to draw this dependency graph, it will not do well, right? Because it has lost some information that it needs to achieve that objective, right? So again, this filtering of what to drop, what not to drop is sometimes application dependent, and you need to be a bit careful about that. Yeah, and the last part is how do you you have cleaned the text, removed unnecessary noise and everything. How do you make it ready for, let's say, a downstream application, right? We'll come to it. Right. So there are a bit more examples of why would you stop and remove stop words and lemmatization, all that. You can go through them, but I am skipping ahead. So here we'll look at some of the ways you can clean your text, pre-process your text, and we will go a bit more beyond tokenization, right? So we'll discuss I think a couple of a few libraries like alphabet detector, tweet preprocess, and ekpheresis. Ekpheresis as a library is something that is very useful if you want to deal with social media text, right? It allows you a lot of control that you might want to need, and all of this is configurable, so you might use it or might not use it depending on the depth that you want to go to, right? So let's say these are the texts that are taken from social media, and you can see that it comes with social media artifacts, right? You have hashtags, you have weird emojis like this, and you have user mentions like this, and URLs like this, right? So this is the kind of text we are dealing with, and just simply doing word tokenize from NLTK or tokenization from spaCy might not be the best idea here, right? Might not tokenize it as you would want. So this is where you can write a function like this, right? So we are using a text preprocessor that is implemented by a library called ekpheresis, right? And this offers a lot many things. I have linked the library. You can go and check it out. But we are dealing with preprocessing and tokenization part of it here, right? So it allows you to normalize URLs, emails, percentages, and such entities. It will also allow you to annotate. So annotate, it means that it'll say that it'll replace that particular string with that annotation. For example, it will replace any hashtag saying that this is where a hashtag was, right? You can segment hashtags, break it down into constituent tokens using the segmenter. You can correct the spellings, right? On social media data, it's not it's a very common thing that the spellings are not always correct, right? So you might want to handle that. And there are and you can also mention which type of tokenizer you want to use. You can use a tokenizer that this library offers. You can also replace it with the NLTK word tokenizer, and this would work the same, right? So you can see that this particular sentence, can't wait is essentially all capitals, right? Now all capitals sometimes is useful information. All capitals could be indicative of an excitement, that somebody is excited about this, or stuff like that, right? So if you're especially mining for sentiment or any effect, and this kind of information could be really useful, right? So and once you are cleaning this, you can see that it has annotated the data as this, right? So it has marked saying this is where an all caps string started and this is where an all caps string ended, right? And it replaced, it basically also marked where a hashtag started and where a hashtag ended, and you can also see that it has broken it down into tokens, right? And also you can see that there are 3 exclamation marks that they were repeated, right? Instead of keeping those 3 exclamation marks, it is basically saying that there was an exclamation mark, but it was also repeated. Now this repetition of certain punctuations like exclamation mark is sometimes also indicative of whether in stuff like sentiment analysis or hate speech or stuff like that, right? So so it's sometimes useful to have this information handy, right? So again, ekpheresis is a library that is allowing you to do a bunch of this stuff. You can look at these other 2 examples as well, but yeah. Instead, if you don't want to deal with such level of complexity, you want to keep things simple, you can also use a tweet preprocessor, and it can also tokenize a social media text into stuff like this, right? So and you can see that here it is replacing Ted Cruz, @Ted Cruz is replaced by a mnemonic mention, and hashtag is replaced by saying that there was a hashtag here and stuff like that, right? So while it is taking away the hashtags themselves or the user mentions themselves, but is maintaining the structure. It is very clearly telling you that there was a user mention here, there was a hashtag here, and stuff like that, right? and that is sometimes necessary. That kind of cleaning is sometimes necessary if you want to run some application on top of text. Right. Next thing is language detection. Broadly speaking, let's say on social network data, you are not always bound. It's not compulsory that you will only deal with English data, right? So if you want to just understand what is the distribution of the distribution of data in a collection of social media text, you can use this. You can use this library called alphabet detector. What it does is that it goes to the string and identifies what all languages in terms of what all scripts were present. Sorry, not languages. What all scripts were present. So here this is a Telugu string, and it can detect saying that there was a Telugu. This string has only Telugu characters, right? Telugu script characters. Here you can see that this is a combination of English Roman characters, Latin characters, and also Devanagari characters. The word PM, MSP are English tokens, are written in Latin characters, and the others are Devanagari, right? So when you say detect the alphabet, you can see that this is a combination of Latin and Devanagari, right? So but again, let's say that if this was a Marathi text where this was PM followed by Marathi text, MSP followed by Marathi text, the output would be the same, right? The alphabets that it would detect would be Latin and Devanagari, right? Because sometimes it is not always a one-to-one mapping between a language and a script, right? Sometimes a script is shared by 2 or 3 languages. For example, the Latin script will be shared between English, French, Spanish, right? And Devanagari would be shared between Hindi and Marathi, right? So sometimes just by detecting the script of the alphabet, you can make out the language, but sometimes it can give you a probable list of languages, right? So Devanagari, by looking at Devanagari, you can say that, okay, this is either Hindi or Marathi, right? So language detection going beyond script is a research problem, and there are multiple libraries that allow you to do that with fair degree of accuracy, and sometimes they work well and sometimes they don't. Right. So we'll also look at some Indic language specific libraries. So we looked at NLTK. There were functionalities like word tokenize and sentence tokenization, and we saw that we know that it is learned on English corpus, works very well for English. But what happens if you're dealing with Indian languages? Let's say English, let's say Hindi, Telugu, Marathi, and any Indian language for that matter, right? So this is a very good library that was created by a researcher called Anup Kunchukutan, and this library has many basic functionalities that you would want when you're working. Definitely want if you're working with NLP data, Indian NLP data. So you have a Hindi string here, and you can basically use the sentence tokenization that is built into it, and there are a bunch of other functionalities like this: word tokenization, sentence tokenization. I have linked the library here. You might want to go and check that. Right. Coming to a bit more complexer case where you have Hindi words that are written in, let's say, Roman script. Mosam is written in the Hindi word mosam is written in Roman form. Similarly, hoga, right? And this is the stuff that is very common on social network. This is very stuff, let's say, is also very common on your own personal messages, IM chats, and places like this, right? So if you're dealing with, if your domain is that, then you might want to be careful of this fact, right? Because NLP pipeline that works very well for Hindi that is there in Devanagari script might not work very well if the Hindi is written in Romanized form, Latin form, right? So there are a couple of libraries, but they are very language specific. There's this one library called CSNLI. It works very well as long as you're sure that the text is English or Hindi, right? So it can for each token it can give you the corrected token or the normalized token. The Hindi word MOSM is corrected to its Devanagari spelling, and you also get, okay, which language does this token belong to, right? This phenomena is called code mixing, very common on social networks, where you are mixing 2 languages and romanizing them as well at times, and this is a phenomena that's a bit harder to deal with. Right. So this is a toolkit that is available, and you can use it for English, Hindi. But let's say if you want to take you run into a text that is a mixture of English and, let's say, Hindi or English or Telugu or English or Tamil, such mature tools might be a bit hard to get by, right? So this is where you would end up training your own models or training your own toolkits, right? So this is where we stop with the text pre-processing stuff, and we'll go into the next part of the tutorial where we look at how do you convert text into features. By features we mean numbers, so that downstream toolkits can process them.